So you might have noticed that the title does not match at all what the program says. This is essentially saying the same thing, but with some specific name. So let me try and introduce what I'm doing. So as the title alluded, I do higher order DG methods. As Ruchao had previously said, these are advantageous if you're using unstructured meshes. If you have some fancy or very complex geometry that you want to mesh tightly, like say this diagonal split in this cube, you can use unstructured meshes to fit this very, very nicely. This is an example of wave propagation. You can catch discontinuities in material data very closely. And also DG provides, along with this sharp discontinuity resolution, high order accuracy. So here's an example of why high order accuracy is important for wave propagation. This is, I'm sure you all know this well already. If you were to evect a wave, this is just a 1D periodic wave, evect it several times. If you use a low order, a linear approximation, then you see that you suffer some artificial dissipation near the tips. If you switch to just one order higher, but actually decrease the mesh resolution, you have fewer degrees of freedom, but a higher order approximation, you see that this numerical dispersion disappears almost immediately. So that's hugely important when you're simulating over long time scales, over long length scales. It's also more accurate per unknown. If you just plot the L2 error or L infinity error, whichever norm you want, you can see that higher order methods, as you go down, they converge at a much, much faster rate. And personally for me, I'm very interested in GPU computing, accelerated computing in general. And if you use explicit time stepping with higher order methods, then they get great performance on these architectures. OK, so what am I interested in? It looks like everything's been solved, right? I want to have accuracy and I want to have efficiency. And the key word here is in heterogeneous media. So one of the downsides to DG compared to finite difference is that dealing with smoothly varying heterogeneous media can cause some issues. We have some recent developments which I think address some of this. First, let me give you a brief, a broad overview of what time domain DG looks like. We take our solution, we approximate it in some basis expansion. Think of this as a polynomial basis. Monomials, orthogonal polynomials, these are nodal polynomials, Lagrange polynomials, because they make our life convenient. Then what we do is we approximate the solution differently on every single element, compute a numerical flux which couples these two elements together and essentially acts as a boundary condition for each local element. Once we have this numerical flux, we can compute the right-hand side of a local ordinary differential equation system. This is just advection, so you have the time derivative, du dt equals du dx, and this is the flux term that couples different elements together. So this first operation is non-local. You have some communication. This operation is local. These are dense matrices, which depend on the order and the size of the dimension of your problem. And then you whack that right-hand side with the GPU and use your favorite SGEM or LAPACK library to do dense linear algebra. So afterwards, you evolve the solution using whatever favorite explicit time stepper you like, and repeat and rinse. So the magic here is that you have this differentiation matrix, dx, and what's called a lifting matrix. If you're familiar with finite difference summation simultaneous approximation terms, this is essentially the DG analog to that idea. OK, so this was for simple advection. I'm going to try to introduce weight-adjusted DG to deal with more complicated problems where you have heterogeneous media and wave propagation, especially when you have arbitrary heterogeneous media, which has both discontinuities and smooth features. And then I'm going to explain why this approach loses some efficiency and how to restore it with this new variant we have called Bernstein-Bezier WADG. OK, so I'm just going to consider the acoustic wave equation right here. I have some wave speed c squared, vary spatially over the mesh. And if I was to just overlay the mesh here, if I approximate this wave speed by a piecewise constant over every single element, and I release a little Gaussian pulse at the middle, then I get this solution. You can see it has some spurious reflections, some weird irregularities that don't really jive with the type of the smooth wave speed that you have here. If you instead use a high order polynomial approximation of the wave speed, then these spurious reflections all disappear. So this is the reason why this is interesting still is because piecewise constant wave speeds are much more efficient to simulate. If you look at most higher order DG codes that are present in seismic communities, they use piecewise constant wave speed because when you use high order wave speeds, you have to introduce weighted mass matrices. So if I discretize this this pressure equation for this acoustic wave equation system, then I end up with an OD which looks like so. So AH just represents this right-hand side, which involves differentiation and lifting matrices. We can ignore it for now because this is fairly straightforward to apply. But if you introduce high order approximations of the wave speed, you end up introducing these dense weighted mass matrix on the outside. this weighted mass matrix, you have to factorize explicitly, you have to store the inverse with the factorization, and it's generally a pain because now you have additional storage and you have to, it's a little bit complicated to do, and if the wave speed changes, you have to repeat the process over and over again, so for FWI this can be problematic. So what we did a couple years ago with Russell Hewitt and Tim Warbert, my postdoctoral advisor, was introduce the idea of weight-adjusted DG. We take this mass matrix, ignore it, and approximate it with this product of 3 mass matrices. So I have this unweighted mass matrix on the outside, left and right, and on the inside I have the inverse of the weighted mass matrix with the inverse weight. So you can think a little bit of this as the matrix version of approximating 1 over c squared by 1 over c, approximating 1 over c squared by 1 over, I guess, c squared. It works out properly. I'm having a little trouble expressing this at the moment. But essentially, this gives you a high order and very efficient approximation to this weighted mass matrix. And you also have the advantage that you can reuse previous implementations. If you have an isotropic wave propagation code, then when you actually invert this mass matrix, you can split off this first term and invert it onto the right-hand side. This is just your implementation for an isotropic wave propagation code. Then you can apply the rest of the mass matrix, this mc squared inverse times m, and modify your update kernel as a post-processing step. So you can take your existing codes, modify them, and essentially get a heterogeneous media code. The reason why this modified update is nice is because you have a very low storage matrix-free way to apply this operator. So instead of actually storing this matrix and forming it, we can simply store the value of the wave speed at quadrature points, which are separate from our nodal points, and then apply 2 matrices, an interpolation matrix VQ, which evaluates your solution at quadrature points, and an L2 projection matrix PQ. I'll come back to these matrices a little bit later. But essentially, this gives you a very, you don't have to store matrices, you only have to store single vectors, so your asymptotic storage cost decreases, and as we all know, for HPC, reducing the amount of memory and data that you use is fantastic. So let me show you that this actually works. Here's, I have a uniform triangular mesh underlying all this, and I have a smooth sinusoidal wave speed with a discontinuity in the middle. If I use standard DG, where I just store the mass matrix and invert it, then I get this solution. If I use weight-adjusted DG, then you can't tell the difference. So visually, that's fine, but we actually have some mathematical theorems and some very recent work that shows why these 2 solutions basically always look the same. The L2 error that you get is essentially order h to the n plus 1. H is the mesh size, n is going to be the order of approximation of your method. We can show the difference between standard DG and the weight-adjusted DG method is actually converges at 1 order higher. The difference between the 2 is h to the n plus 2. So visually, they are always identical. And if you're interested in elasticity, I have a paper here where we generalize the whole thing to matrix-valued weights, and you can apply this to linear elasticity in a very nice, efficient fashion. OK, so let me talk a little bit about efficiency. This is more efficient than storing the inverse mass matrix on GPUs, mainly because you reduce the amount of data that you need to load. Here are runtimes for either storing the matrix or using weight-adjusted DG. I've tuned both these kernels, so weight-adjusted DG uses data locality. It processes more than 1 element at a time, and then uses the low storage nature to get a little speed up. So you can see that for low orders, the speed up is modest, 1.1. As you increase the order, the speed up goes to around 2. If you increase the order to 3, your speed up stays around 2.3, goes to 2.6. If you go high enough orders, then you eventually find that the weight-adjusted DG is still faster, but a little bit less fast because the cost of weight-adjusted DG increases very rapidly with the order of approximation. This is also true for storing the mass matrix. These are shared issues. Basically, high-order DG methods are very accurate. They're advantageous in many respects, but they are expensive. And this is primarily what I want to address with this new method. The weight-adjusted DG method is accurate, but costly. So here's an example of the runtimes for the 3 kernels which are involved in my wave propagation solver. I have the update kernel, a surface kernel, a volume kernel, and as you can see, as I increase my degree, the runtime just blows right up. So this is mainly because DG methods involve lots of dense matrix multiplications. Finite difference methods, they involve sparse operations because you have the stencil and you only really have to deal with some very small amount of neighboring information. As you increase the degree of your DG method, you couple together, you have to multiply by a matrix which is fully coupled. So all the degrees of freedom on one element have to be involved when you try and evaluate the right-hand side. If you use something like spec-fem or DG-SEM, then you can decrease this cost from order n to the 6th in 3 dimensions to order n to the 4th, but you then have to use hexahedral meshes. And these can be problematic when you're trying to do some of the tricks that Ruchow showed you where you're meshing to very complex salt bodies and so on. So our idea was to simply choose a basis such that the resulting matrices that we have to multiply by are sparse. So let me try and illustrate. These are nodal bases in 1, 2, and 3 dimensions. If I can plug them into a DG method and get something that looks kind of like I get a semi-discrete ordinary differential equation with 3 matrices that I showed you before. These cost order n6 to apply. So what I'm going to do is switch to a different basis, a Bernstein basis. This is just a change of polynomial basis. Approximation space is all the same. It's exactly as accurate. You should get exactly the same solution. But what happens is if you look at the matrices, they become really, really sparse. These are the differentiation matrices for Bernstein bases, and you can actually bound the number of non-zeros per row by d plus 1, where d is the dimension that you're solving in. So these are fantastic for GPUs. You just store the values and the column IDs, and you get a very, very efficient lookup. You reduce the amount of memory you have to load from global memory by a huge factor. The lift matrix is a little bit more complicated, but essentially we have a an optimal complexity, order n to the cube, slice by slice way to approximate it, which uses also sparse matrices. If you're interested, there are some details in the CISC paper, and I can also talk to you later. So what does this actually buy you? Here's the chart of the runtimes for the volume and surface kernels for nodal DG when you're using dense matrices. You use Bernstein-Bezier DG, and this runtime just drops flat as you go higher and higher order. You gain a significant amount of runtime. You can look at the speed up, and you essentially become up to 6 times faster at higher degrees. And if you want to go even higher than this, then you gain even more. So if you're trying to use a degree 10, 12, 14 DG method, I would highly recommend Bernstein-Bezier DG methods because they buy you a lot of efficiency at higher orders. So the downside is that this deals with the volume and the surface kernel. This doesn't deal with the update kernel, which is where we apply our weight-adjusted approximation. And this is some new work that my student Kai-Hong Guo has done, where with weight-adjusted DG, we can reuse fast Bernstein volume and surface kernels, but we don't have any way to deal with the cost of the update kernel. The cost mainly comes in where we're multiplying by this matrix VQ, which evaluates things at quadrature points. And then when you're applying this, this projection matrix, PQ, these are 2 large dense matrices, and there's no real structure that comes out when you're using Bernstein polynomials here. So instead, we chose a new approach. Let's take our c-squared, some smooth function. We'll approximate it by polynomials, a degree m polynomial. So if you take m equals 0, you just have a piecewise constant approximation. If you take m equals 1, which will be our focus, you have a rough but more accurate approximation, piecewise linears. So once we have this, then our whole goal is going to be to multiply our solution, u, by some wave speed c-squared. And we can do this using fast polynomial multiplication algorithms and a fast projection algorithm, which we invented for Bernstein polynomials. This is a very picturesque slide. If you want to let's say this is a representation of a degree 1 polynomial on a tetrahedron. You have 4 degrees of freedom, and we can multiply it by, I think this is a degree 4 polynomial. And if you were to actually write this in algorithmic terms, this is equivalent to taking these 4 sparse matrices, multiplying the solution by them, and then scaling each of them by one of these degrees of freedom, C1, C2, C3, and C4. This, as long as you keep the order m fixed, is optimal complexity. This can be done very, very fast. So that's half of the formula for weight-adjusted DG. The other half is doing this projection very quickly. And that's a lot more difficult, but there is an approach that we found to do it. So our whole goal, as I said before, is once we've done polynomial multiplication to represent the product of the wave speed and our solution as a degree n plus m polynomial, we now want to do the L2 projection to project it down to a degree n polynomial using some matrix Pn plus m Pn. So under a Bernstein basis, you can decompose it into what are called degree elevation operators. So they take a degree n polynomial and represent it as either a higher degree or lower degree polynomial. The advantage of these things is that they're also sparse, and they can be applied very rapidly. So this matrix on the outside is pretty easy to apply. It's fast. And what we're dealing with is really this summation of matrices on the inside. We can rewrite this in what I call a telescoping form. And essentially, you can apply this in order n to the fourth complexity. This form is a little bit more GPU friendly. And just to try and convince you of that, here's a picture of the algorithm. What you essentially do is you have order n cubed threads, so one thread per degree of freedom. And then you store your solution in shared memory. You apply these degree elevation matrices n different times so that you reduce your vector of degrees of freedom down to a smaller vector, down to a smaller vector, and so on. This can all be done in place in memory, so you're not increasing your memory cost. At every single step, you save something to register. So you have order n register memory per thread, because you're going to need this later on. So once you've reduced down to your lowest degree, then you elevate the solution back up, and then use this stored register memory to compute this overall projection. We have the code. It will be publicly available online by the end of summer, but I'm happy to tell you more about it if you'd like. So what does this actually buy you? We're comparing piecewise constant approximations to piecewise linear approximations to full higher order approximations. And it turns out that piecewise linears buy you more than you expect. So if I look at the convergence of a model of a manufactured solution, then if I represent the wave speed using piecewise constants, I get order h squared, or quadratic convergence, or quadratic convergence. If I represent it using piecewise linear polynomials, then I actually see that I get order h to the fourth, so I get quartic convergence. I get more than I expected. If I then represent it with a higher degree quadratic polynomial, I actually only get quintic convergence. So I gain 2 degrees of convergence when I switch to linears, and I only gain 1 degree of convergence if I switch to quadratic. So linears, at least in my mind, are kind of like the sweet spot where you can get, where you can minimize the computational work, but maximize the amount of accuracy that you have. So what does this buy you in the end? This is the actual runtime for the update kernel. So we already have speedups for the volume and surface kernels, but if you look at the runtime for WADG, you can see it blows up at higher order. It actually doesn't even run past 8 because we don't have enough threads to deal with the number of quadrature points that are present for these higher orders. So you see the runtime explode, and then the runtime for WADG, it's slower at moderate degrees, but at 4 it crosses over, and you can see that the asymptotic runtime matches this order n to the fourth curve that we have right here. So if you're going to do higher order with WADG, you can get some pretty significant benefits. If you look at the speed up for n equals 3 for a cubic approximation, it's slower. For n equals 4, you match. For n equals 5, you're 1.65 times faster. N equals 6, 2 times faster. N equals 7, 3.5 times faster. And then you have this massive jump at n equals 8, where you suddenly become 23 times as faster. And this is a little bit artificial. I just want to warn you, because the type of quadrature that you need when you go to higher and higher orders, we don't have nice quadrature points for n equals 8. We switch from having this very even distribution of quadrature points to having this set of quadrature points which are basically defined on a cube grid and then collapsed. So there's some artificial expense involved in n equals 8. I just want to point that out. But you do get some increasing efficiency as over regular WADG as you increase the order n. So let me just conclude by saying, if you're interested in heterogeneous media and you're doing moderate low orders, then weight adjusted DG gives you efficiency. And we didn't stress this, but it also gives you stability. You can prove that your solution isn't going to blow up. Things are energy stable. This was very important to us when we were formulating it. If you're interested in very high orders, you can maybe check out BBWADG or Bernstein-Bezier WADG, which gives you improved complexity if you approximate the wave speed. And finally, I would like to thank the National Science Foundation, who has been very generous in funding this research. And I welcome any questions. Thank you all for listening.
Let's limit it to one question.
Yes.
OK, let's say I making a mistake when I'm meshing, and I mesh over a discontinuity. How would that impact the convergence results you just showed?
Yes, very good question. So you would lose convergence. You would basically degrade down to quadratic convergence, order h squared. But if you were to compare high order resolution of that discontinuity with low order resolution, like the piecewise constant case, you would see about a 10 that your error would be about 10 times lower. Given this is all for 2-dimensional and 3-dimensional manufactured solutions, so I'm not sure how it would really behave for a much more complicated model with multiple discontinuities. I've just investigated 1 or 2. Thanks.
Speaker again.
Thank you all.